Okay, so in last session we discussed about classification, and we discussed that in classification we have output variable as a qualitative variable. They have some discrete values, and they can form some classes in order to put these values into it. Now we discussed about logistic regression, which is preferred for k equal to 2 classes, where we also saw that for using the linear regression we have some problems over the endpoints, and we decided to make a function which lies below them, and this function tries to give us the direct value for k equal to 2. Now we also discussed that we will have some models for k equal to 3 or k greater than 1, which will also include values for more than 2. So we will discuss about linear discriminant analysis. I also said that every classification model has some generalized assumptions with them. So in linear discriminant analysis, what we try to do is we will not try to have some function which will directly lead us to the conditional probabilities. Instead, we will directly handle these conditional probabilities using the x and y values. So we will not generate some function which will help to classify into 4 values or 3 values, which will directly lead us to the conditional probability. Instead, we'll design the probabilities, we'll find the distributions of these functions, and then we'll directly handle with the conditional probabilities. So our basic assumption in linear discriminant analysis is that our distribution of all these points are normal. So all the x variables are normally distributed, and then we proceed with the conditional probability. Now in order to check whether our distribution of variables are normal, so we plot a QQ plot, normal quantile plot, where these are the quantiles of the normal distribution, and this is our data set. So we'll try to plot the quantiles of the normal distribution with the sample data set, and if we get a straight line, then we assume that our distribution is normal. There are various other assumptions that we can make. Suppose if a data points form a convex shape, then it means that our distribution is quite skewed, so it will be left skewed. And if our distribution is concave in shape, then we'll say the distribution is this way. There are two other more shapes also. Suppose we have a vex cave shape, convex concave shape, then it means that we have a higher, very heavy tails in our distribution. And if it is a cave vex or concave convex type of shape, then we will have a light tails than the normal distribution. So in this way we can find out whether a distribution is normal, and we can also interpret some of the properties of if there are some tails or skewness in a distribution. Well, there are more ways to find out. One is the Shapiro-Wilks test and the KS test or Anderson-Darling test. So these tests help us to find whether the sample which we are taking from the population, so whether the population is normal or not. For them, these tests are required. We will discuss about the KS test towards the end of the session, but other tests are usually not required from this point of view. So we'll start from the Bayes theorem. So Bayes theorem says that P of y given x is P of x given y upon P of y by P of x. So let's say we have two sides, one is training side and the testing side. So in training side we have the y values with us, and all the x predictors also. So suppose we have the y values and we try to find the clusters in the y, and using these different clusters of y, we try to model how the x's are changing. So we try to find the distributions of the x which gave us the value of the y. So that is p of x given y. We know the event of y has happened, and we are trying to see what is the probability of x. And the probability of y is what is the probability that each point will get into, each data point has the probability of getting into first cluster, second cluster, third cluster, and so on. And the p of x is actually the summation of all the x points in these clusters. So what we are getting is that we are getting a probability of getting into the class. K classes are there, so usually if they are equally distributed, we'll have a probability of 1 by k, and the distribution of x to get the y model. So this will be usually the PDF of the distribution. In the LDA case, it will be a normal distribution, and for the distribution of probabilities of x, we have the summations of the classes to have the x points. So this will give, for the testing side, that we have the values of x, now predict the values of y. So we'll get the probabilities of y using this Bayes theorem, where we already have the training data and we already have these values. So we already did the probability distribution, and we have the PDF f of x value of the normal distribution. So we'll put the values in them, and what we'll do is we'll take the log of this equation and equate it to 0. We'll get a line equation, a linear equation if line, which will help us to tell us the boundary of these classes. So for example, let's say we have these two distributions, x1 and x2, and we need half of the data, let's say the data points can either belong to this normal distribution or this normal distribution. So when we take the log of it and we find this linear discriminant function, this function, when we put the values of class 1 probability and class 2 probability, let's say the probability of getting into class 1 and class 2 are same, and that is half. So when we solve in this equation, we will get a discriminant value as nu1 plus nu2 by 2. So that will be the mean of these two values, which will be around in the center. So what this tells is that when we have the equal probability of lying into one of these two normal distribution clusters, and when we put these values of probability of getting into these clusters, we get a boundary equation, and this boundary equation helps us to identify or differentiate between these two clusters. Now suppose if we have suppose if this cluster is getting bigger, now the probability of getting a data point in this cluster will be much more larger. So this boundary will start shifting towards this direction. So as this normal cluster will start getting bigger and bigger, the boundary line will start getting towards the left hand side. So in this way, the probability helps us to find the boundary line equations between the two variables, between the two distributions or clusters. Now similarly, this is a situation where we have a single x variable, single predictor in a model. When we have multiple x predictors, as usually we have, what we do is we use this equation where this sigma is actually the covariance matrix. We have a covariance matrix between all the x variables, and in this way we can find the discriminant function for that. So it is this. So this is the discriminant function for the multiple variables. Now in LDA, what we did is we assumed two normal things, that one is the distribution. Let's say this is an x1 variable and this is an x2 variable. So what we assumed is that these two variables are normally distributed, but they have equal variances and they do not have any correlation between them. So this normal distribution, when we cut from here, we get a straight circle cross section of them, but usually it is not the case. Whenever we are having multiple variables, they tend to have some correlation and they may not always have the similar variances or the same variances. So let's say this is x2 and this is x1. So as we can see, this distribution is having a larger variances than this distribution of this normal distribution towards from the x2 side. So what happens is the sigma 1 square and sigma 2 square are not equal, or they may have some correlation between them. So what happens is that while finding the discriminant function, all these parts, all the coefficients of sigma do not cancel. So what happens is we get this part extra when we have the correlation of sigma square term unequal, not equal. So because this term we have an extra in the discriminant function, when we see this x multiplied by this x, so we get an x squared term. So this equation is actually a quadratic term, and that's why having this discriminant function due to not equal variances or correlation is called a quadratic discriminant analysis. So QDA helps us when we have a correlation or some different variances among the different variables for the normal distribution. Now this is a confusion matrix. This is called a confusion matrix, and one of the most important point is this is a binary classification matrix. So what it means is that when we are having a confusion matrix, we need either positive or negative values. So positive means, let's say in case of the credit card default, positive means that the person will default, let's say, and negative means person will not default. So this is a way to evaluate whether a model has properly predicted or forecasted and understood the differences. So what we will do is we'll define the positive and negative, and it will have a binary classification between positive and negative, not more than them. So what happens is this box, this column, what will happen is predicted positive. So what is this is like what a model has predicted as the person will default. So this is the entire box. It says that the person will the number of people will default, and we have divided these boxes into two parts. One box is that they actually defaulted. So this box gives us the number that the number of people have actually defaulted, and this box gives us the value which says that the people have not defaulted, but a model says so. A model has labeled them as the defaulters. Similarly, a model says they will not default or negative, and they are also divided into two parts. So this says that the person will default, person will not default, but they actually defaulted, and this says the person will not default, model says the person will not default, and they didn't default. So what happens is the true positive and true negative are the values which the system and the reality coincide. So a system said the positive will default, and in reality they defaulted. So this box and this box, true negative and true positive, are the number which the system predicted correctly. Now how to understand these labels? So when we say true means correct, and when we say false means something is wrong, it's wrong. So when we say true positive means that the value or the labels which are positive were correctly or truly predicted by the system. Similarly, when we say negative and true negative, it means that the negative values were correctly predicted by the system. Similarly, false means something is wrong. So what values we predicted wrong are positive values. So false positive means that we said, the system said, the model said that it's a positive result, but actually in reality it was a negative result. Similarly, false negative means that we predicted something wrong, and what we predicted wrong was false negative. So negative values were predicted wrong, they were actually positive. Now there are various ratios to understand, and there are various ratios which we take out from them, and we try to interpret how our model classification has been working. So the first is the sensitivity ratio. The sensitivity ratio is the true positive which we correctly identified versus the divided by the true positive plus false negative. So true positive plus false negative. So what this means is that if sensitivity is equal to 1, then this number should become 0. So if this number becomes 0, that means that we didn't predicted any positive value, the system didn't predicted any positive value as wrong. So all the people who actually defaulted were correctly being labeled by the system. So we didn't have any false negative values. The second is 1 minus specificity. So 1 minus specificity, sensitivity and specificity. So we'll look at the specificity first. The specificity is true negative divided by the true negative plus false positive. So what this is saying is that how many values, how many negative values, negative label values we predicted as correct divided by the total number of values which were actually negative. So this is for the positive correct labels, and this is for the negative correct labels, and this is quite intuitive. When we look at this confusion matrix for some time, these all ratios will start becoming very intuitive and very easy to understand. Similarly, 1 minus specificity is false positive divided by the total number of actual negative label values, and accuracy is these two boxes which were correctly identified versus the sum of all the boxes. So as these two boxes, these false positive and false negative boxes values start decreasing, the accuracy of the model and rest all the values, sensitivity, specificity, etc., these values start increasing. Now let's say we have let's take the case of default of credit card. So let's say we have this as not default and this as default. So these are the two distributions of predicting whether a person has defaulted or not, and these are the two classes actually. So this is 0 and this is 1. So this is the person has defaulted, this is not defaulted. As we can see in these three distributions, the first model has tried very nicely to separate out the defaulters from not defaulters. This has done a okay job to separate these two classifiers. So the classifier has done a fair mediocre job in order to separate the non-defaulters from the defaulters, and this has done a terrible job. There is much more overlap between the prediction for defaulters and non-defaulters. So how we are, let's say the sample size was 100 for non-defaulters and 100 for defaulters. So let's say this is the probability line. So let's say we have 0.1. So this says that this is 5, this is 15, and this, let's say this is 25. So this 0.1, so what this model says is that there are 5 people having 0.1 probability which are not going to default. So if there are 5 people in the model, in the data set having 0.1 probability, so the model says that they will not default. Similarly, 0.2 probability, there are 15 people which the model says will not default. Similarly, 25 people with 0.3 probability, the model says they will not default. And here let's say we have 5 people at 0.5 probability, 10 people at 0.5 probability, then they say that 5 people of them are going to default and 5 people of them are not going to default. Similarly, this is 0.7 probability, there are 25 people with 0.7 probability, the system says all of them will going to default, and so on and so forth. So we can see as this area of overlap increases, the confusion of the model, that out of them half are gonna default or not default, is gonna increase. So here we have only 5 people that the model can't say which are gonna default and not. Here we have 10 people and here we have 20 people. So in this way the classifier accuracy we can determine. Now as you remember, I discussed in the logistic regression that we had probability of default y equal to default given amount, and I said that we can change the threshold of amount to greater than 0.5, 0.6, etc. We can change the threshold in order to if we are having the number of defaulters or false positive rate or true positive rate as very less or more. So we can change this threshold and we can change the true positive rate or false positive rate of the model. So let's understand how is that going on. So let's say we have a threshold over here, we have a threshold over here and we have a threshold over here. So let's say this is a threshold of greater than 0.5, this is a threshold, let's say, greater than 1, and this is the threshold which is greater than 0. So if we say that amount is greater than 0, then the person should be a defaulter. So the area, this area is actually of non-defaulters and this area is actually of defaulters. So how do we find the true positive rate and false positive rate? Is like, suppose if we have a true positive data set, let's say this is a blue area and our threshold is over this side. So what we do is that whenever we get a probability more than this line, we label it as a positive, and when we get over the left hand side, we say it is negative. So if the entire curve is actually the positive, so the ratio of how much true positive rate is going to be there is simply the area of this divided by the entire area. So let's say this area is 50% and divided by 100, so we are going to have 50% true positive rate. Similarly, when we have a line over here, so we are going to have 80% of the entire positive rate to be correct. And similarly, as this threshold changes, we are going to have a different positive rates for all of them. So this red curve is actually for false positive rate because the false is for non-defaulters, and this blue curve is actually for the true positive rate because this curve actually determines how many people are gonna default. So what we are going to do is we are going to start from here, and let's say any point from here, from 0 greater than 0, we are going to have a default as 1. So we are going to say that person has defaulted. So we can see that the entire area of blue is actually on the right hand side. So we are going to label all of these as defaulters. So what we are going to have is that we are going to have true positive rate as 1, but we are also going to have a false positive rate as 1 because we actually labeled all of the non-defaulters also as true defaulters. So this entire false positiveness, we determine all the false positive as true positive, so our false positive rate is also equal to 1. So we label, this is the ROC curve and this is a 1 by 1 curve. We label them as 1 and 1. So this is the false positive rate and this is the true positive rate, TPR. So when the threshold is over here, we are going to have the false positive rate as 1 and true positive rate as 1. When we have a threshold over here, let's say from 0.5 greater than 0.5, so what we're going to have is the red values towards the right and the red divided by the entire red values. So red values towards the right are, let's say, 1%, and red values towards the left are 99%. So red values we have is 1% values we have divided by the entire red value of the cluster. So we are having 0.01 value. And similarly for the blue curve towards the left divided by the, let's say this is 99%. So we are going to find the blue curves towards the left divided by the entire blue curve, area under entire blue curve. So area under entire blue curve is 100%. We are assuming this area is actually 1%. So what we are going to have is 0.99 and 0.01. So we'll plot some 0.99 and 0.01 on the curve, and as we move towards this side, we'll have a blue curve on the right hand side divided by the blue curve, entire blue curve. So in this way we are going to plot the TPR and FPR. FPR is the red curve on the right hand side divided by the entire red curve. So what we are going to have is, as this threshold, let's say have another diagram, as this threshold moves from here to this side towards the 1, of the towards the end of the blue curve, we are going to travel from here to here. So the entire TPR and FPR are going to change in this fashion from right to left. So this FPR is going to decrease very fast from this value to here, because here we all have are the true positive entries. So as we are increasing the threshold for true positive entries, our FPR decreases extremely fast. Okay, this is the false positive entry and we are starting from here. So as we move from here to here, not here to here, we are moving from this side to this portion, our false positive entries are gonna decrease extremely fast. So we can see we are moving from here to here without changing much of the true positive rate. As we move from this part towards this part, towards this end, we are seeing that we are actually increasing the threshold for predicting the true positive values. So as we move from here to here, our true positive values start increasing extremely fast. As we can see from this point, this threshold will reach almost over here, and from here we are going to fall extremely fast, because we are going to label these all points as the threshold moves towards right. We are going to label these all points as the red cluster, that they come under the red cluster. So we are going to have a very less true positive rate. Now as the area under this classification is under the overlap part, where we are not able to distinguish between the defaulters and non-defaulters, this curve starts getting downwards from the corner. So here, since we have a very clear-cut distinguish between red and the blue curves, our curve is almost touching towards the corner. As the area between the overlap is increasing, our distance from the corner starts increasing. Now this is actually a square of 1, as the sides are 1. So the area under the curve is actually the percentage which we are going to find for the accuracy of the model. So this box is actually 1, and let's say this is 0.90. So this 0.90 is actually the area under the curve. So we can see in ROC curve various area under the curve. So when we have area under the curve is 0.5, then it means that we are randomly guessing of these points, and our model does not understand anything. As the area under the curve increases, our accuracy starts increasing. As this reaches almost to the corner, the area is 99.6. Now there is another way, another measure also, that's called F measure. The F measure is actually the precision and harmonic mean of precision and recall. As we can see that precision is actually precision and recall. So precision is actually true positive divided by the true positive plus false positive. So this means that how many values the model predicted correctly versus how many values were actually correct. So true positive is how many were correct and how many were predicted as correctly. Similarly, true positive upon true positive plus false negative is how many I predicted correct were how many versus how many were actually correct. So when we take the harmonic mean of these two, we get an F measure. So F measure actually lies from 0, F less than 1. So this is also one type of measure which we use for comparing the model. The KS statistics, Kolmogorov-Smirnov statistics. So in this, what we do is this is a non-parametric test. So when we have some data set, we plot its CDF, cumulative distribution function, and we also plot another cumulative distribution function of known function or another data set whose distribution or parameters we don't know. Let's, for simplicity, let's say this is a distribution function, cumulative distribution function of the known function, and this line, this blue line actually represents the cumulative distribution function of our data set whose distribution is not known. So what happens is, when we plot them, we try to find the maximum distance between these two lines. Let's say this point, at this point we have the maximum distribution. So what we label it as d, distance d, and then we try to find the hypothesis. We give the null hypothesis as these two distributions are equal, are same, and then we find the p-value for that the distance we find the p-value for the distance, that if the p-value is less than 0.05, then we have no confidence that these two distributions are same, or when they are greater than 0.05, some confidence that then these distributions are similar. The last is actually finding the lift and the gain values. So what happens is, what we do is we will find the gain, and then from the gain chart, cumulative gain chart, we'll try to find the lift chart. So these lift and gain chart are also used for the evaluation purposes. What we do is, first we try to find the data for which our sensitivity or prediction was extremely accurate. So what we do is, we divide the data into some deciles. So every 10 percentile of data we try to divide, and then we try to find out which decile, for which decile or for which group we have predicted extremely well, and then we try to plot these deciles in an descending order. So let's say we have the first, let's say 1000 data points we have, and we predicted, and our response or the sensitivity was much higher. So let's say 30% of the predictions which came are from the first 1000. Then we are going to do is, we are going to have the cumulative addition towards this. So in the end, let's say we have 10,000 data points and our prediction response was 100%. So we are going to add, let's say another 1000 data points, let's say 2000, and the next best prediction or sensitivity which we had is 10%. So what we are going to do is 30 plus 10 is 40%. We are going to add, keep on adding, and we are going to have the cumulative distribution for them. So let's say when we plot these deciles, and for the first one we got the 30%, and for the second one we got the 40%, etc. So what we are going to do is, we are going to plot these charts, and we are going to have the cumulative gain chart. So this is used to find out how well our model has started predicting and how was it got as the last decile. Similarly, there's a lift chart. The lift chart is simply the ratio of this divided by this. So this is 30% divided by 10%. So 3 was the value, sensitivity divided by the population. The next was the 10, because 40, the next increase was 10%. So we go for the 1, and then was 0.5, 0.4, etc. So we are going to have a lift chart in this fashion and gain chart this way. So the more it gets higher and higher, means that the more prediction, more response the model has given up. As we had in continuous distribution, we discussed about the R square. There are few more ways to evaluate the continuous target variables. What we discussed before were actually for the categorical variables. I have decided to add few 2 or 3 points for the continuous variable also. So for the mean, this is for the continuous, not for the categorical. So we already discussed R square, F statistics, etc. for the during the time of the linear regression. These MSE, RMSE and mean absolute error can also be used as the evaluation measure. Thank you.